Hi all, good evening. Wish you all a very, very happy new year. What we're going to be doing in this session is basically this. I keep getting a lot of feedback from students saying that it's been 10 years, it's been 5 years. Some of them even come back telling me that I just graduated 3 months back and I've forgotten whatever I have studied. And therefore they feel that getting started with GMAT Quant is going to be difficult. Just want to break that thing. Let's get started. I want to make this available on YouTube. So like any of you can go and refresh your basics. You're going to be looking at absolute basics today. Get clarity on definitions, get clarity on how to prime factorize numbers. This is going to run into 2 or 3 sessions. One today. The second and third, if it spills to a third, will happen in February and in March. We'll look at only the absolute basics. The remaining thing will anyway get covered as part of the course or as part of the classroom program. Right? This is like a primer. This is like to help us get started. Without taking much more time of yours, we'll get started. I'll share the slide screen with you and we'll start with the definitions of numbers. Right? Just give me a minute to get started. It all starts with definition. It's very evident, obviously, that in the GMAT, no one is going to ask you to define numbers, but this could be presented as part of a data sufficiency question. So knowing those types of numbers and getting clarity on them is very, very evident. Many times we come back not knowing whether 0 is positive or negative, 0 is even or odd. So to get all of these things in place, let's start with the definitions. Start with the most cohesive classification of numbers, the elementary one, which is natural numbers. 1, 2, 3. Full numbers that are positive numbers are called natural numbers. If you include 0 to this set, then it becomes whole numbers. 0 and the set of natural numbers will become whole numbers. Now, if you include negative full numbers, then it becomes integers. Minus 50, minus 20, minus 2, 1, 0, 1, 2, 3. All of these are integers. These numbers would be negative integers. These are positive integers. Now, the next higher classification would be fractions. Minus 50 is also a fraction. In this case, the denominator essentially is 1. All integers, whole numbers, and natural numbers are fractions, and they are obviously called as rational numbers. What are rational numbers? Simply put, they are nothing but fractions. Right? All integers will have a denominator of 1. 14 by 3 minus 78 by 7. Right? All of these are rational numbers. Numbers which are not fractions are called irrational numbers. What kind of numbers are irrational numbers? Something like a root 2, root 7, cube root of 29, certain special numbers like pi. Some of you might be wondering, pi is a 22 by 7. 22 by 7 is a rational approximation for pi. So pi per se is an irrational number. 22 by 7 definitely is a rational number. 22 by 7, pi is not equal to 22 by 7. Pi is approximately equal to 22 by 7. So have this perspective in mind. So square root of non-perfect squares, cube root of non-perfect cubes, these are called irrational numbers. The set of rational plus irrational numbers, this entire set taken together is what is known as real numbers. So you could have negative integers, you'll have a 0, positive integers, positive fraction, negative fraction, irrational numbers. All of these are real numbers. What is the definition of a real number? A real number is 1, which when you square it is going to give you a positive number. Pick any of these numbers and square it, you won't get a negative number. So that's the definition of real numbers. So what are not real? Those are called imaginary numbers. I said if you square a number, it should give you a positive number. Such numbers are real numbers. Let's take this number, square root of minus 7. When you square it, root of minus 7 whole square will give you an answer which is minus 7. So we squared this number, but we got a negative number. Squaring a number, and if it's a real number, it has to be positive because you got something that is negative. These numbers are not real numbers. They are called imaginary numbers. They are represented by, for example, a 5i. The value of I is equal to square root of minus 1. So this is the basic idea behind it, right? So real numbers, imaginary numbers. Don't bother too much about this imaginary numbers. Just for classifications, we are doing it. GMAT, GRE, all of these examinations are going to be restricting their testing to real numbers. So these are the classifications of numbers. So if someone says rational numbers, should immediately know what we are talking about. Let's move on a little deeper into looking at this set. Let's look at what are rational numbers and what are irrational numbers. Rational number, the definition, any number that can be expressed in the form P by Q, where both P and Q are integers and Q is not equal to 0. Anything that you can write as a fraction, the numerator and the denominator of the fraction should be integers. The denominator should not be 0. Such numbers are called rational numbers. When expressed as a decimal, how do these rational numbers look? These rational numbers, when expressed as a decimal, will be one of the following two. They'll either be terminating decimals, something like a 5.2, this is rational. A 9.85, this is rational. Are integers rational numbers? Obviously, we've seen them. Is it a terminating decimal? A 5 is a terminating decimal. It is not going infinitely. So they will be terminating decimals. So go back to the first point, that for all integers, whole numbers, natural numbers, are rational numbers. So they will be terminating decimals. What if they are not terminating? They could also be not terminating, but if they are non-terminating, they'll have this condition attached to it, which is they'll be recurring decimals. So non-terminating recurring decimals, how do they look? Something like a 0.3333. This goes on to infinity. What is the value of this? This is equal to 1 by 3. Is it a fraction? Yes. Therefore, this is a rational number. So rational numbers, when expressed as a decimal, will be one of these two. They'll either be terminating, which means there is a finite number of digits after the decimal point. There can be nothing after the decimal point. So an integer definitely is a rational number. If it is non-terminating, if it goes infinitely, then it has to be recurring, which is when it's going to be a rational number. Something like a 1 by 7, you might think it is not repeating, but it actually is. Just take a look at some number like this. 1 by 7 is a 0.142857, 142857, and it goes on. So it repeats at the end of the 6th digit. It could repeat at the end of the 3rd, 1st, 6th. It doesn't matter. As long as it's recurring, it will be a rational number. So what are irrational numbers? Irrational numbers are numbers which cannot be expressed in the form P by Q, where both P and Q are integers and Q is not equal to 0. Expressed as a decimal, how do these numbers look? Expressed as a decimal, these numbers will not be terminating. First and foremost, they'll be non-terminating necessarily. And they will also be non-recurring. Something like a root 2, the value of root 2 is 1.4142. All our life, we would have probably seen this number as 1.4142. This is not terminating. This is non-terminating. This goes to infinite digits without any pattern of repeating. So such numbers are irrational numbers. So rational, irrational, we know what they are by definition. We know how they look when expressed in terms of a decimal. Let's move on further. Let's look at another very, very important definition. This comes to haunt you more often than not in the entire number property set, which is prime numbers and composite numbers. All of us know what prime numbers are, but let's get the definition crystal clear. Prime numbers, these are the examples 2, 3, 5, 7. What is the definition of a prime number? A prime number, we'll start with this. It's a subset of natural numbers. So you won't have negative prime numbers. They have to be positive. They are positive integers. So it's a subset of natural numbers. And these numbers have exactly two factors. One is 1 and the other is the number itself. Look at any of these things. We know these are prime numbers. 2 is the smallest prime and it is the only even prime. Because any other even number, for example, let's take an 8. What are the factors of 8? Definitely 1 is a factor, 8 is a factor. Forget everything else. Because it's an even number, 2 will be a third factor, which means this number has got more than 2 factors. It cannot be prime. So with the exception of 2, none of the prime numbers is going to be even. All other prime numbers are odd numbers. Now, what are not prime? Very wrong question to ask. What other type of numbers are there? We'll call them as composite numbers. These are all composite numbers. So what is the definition of composite numbers? Composite numbers are again subsets of natural numbers. And these numbers should have a minimum of 3 factors. They should have at least 3 factors. They have 2 factors, then they are prime. There are 3 or more factors. These numbers would be called composite numbers. Have we covered everything in the natural numbers? No, we have not. We said numbers which have 2 factors. We said numbers which have got more than 2 factors. What about 1? Is 1 prime or is it 1 composite? How many factors does 1 have? 1 has only 1 factor. So it cannot be prime. It is not prime because it's got only 1 factor. Is it composite? If it's got only 1 factor, it's not got 3 or more factors. So it's not composite. So 1 is neither prime nor composite. So get these little definitions in place. It'll be very useful in a data sufficiency question. You might think that they would have mentioned something as a prime number or a composite number, or they'll say it's not prime. When they say it's not prime, we'll immediately think of the number to be a composite number. It need not be. It could be a 1. 1 is neither prime nor composite. Not prime does not immediately mean composite, right? So keep this perspective in mind. The next important question, how do we find out whether a given number is a prime number? 2, 3, 5, 7, all of us know these are all prime numbers. So they give you something like 103. How do you figure out that 103 is a prime number? It's a 4-step process. Start with this. Definition of a prime number is it should have exactly 2 factors. One is 1, the other is the number itself. So if I'm taking something like 103, I need to check out whether numbers lesser than 103 can divide 103. So how far should I go? Should I go up to 102? Obviously, all of us know 102 is not the answer. Some of us would have quickly figured out that half this number is probably where we need to go. You don't even need to go that far. The place where you have to go is basically the approximate square root. So till which number do we have to check out? Check out up to the approximate square root of the number. So let's take a 103. What is the approximate square root? Integer level square root of this number is 10. Approximated. Don't try and spend time finding these things out. These are not worth it. Whether you go with a 10 or 11, it makes no difference. It's probably one additional step to check. So don't invest time on this. Don't fret over this point. 10 or 11, both are good. Second thing, now we need to check out all numbers up to 10, whether they'll divide this 103. That's one way of going about it. Is it the most efficient one? No need. You don't need to check for all numbers. Just check for the prime numbers up to 10. Why is it so? If a number is not divisible by 2, the number cannot be divisible by 4, 6, or 8. So checking for 2, and if you figure out that it's not divisible by 2, there is no hope of that number ever being divisible by a composite number. Primes are the building blocks. So it's sufficient if you check only for the primes. What are the prime numbers up to 10? 2, 3, 5, 7. So to verify whether 103 is a prime number, all that I have to look at is only 4 numbers, right? We are not looking at 51. We are not looking at 102. We are just looking at 4 numbers. Next, what? We need to check out whether any of these 4 numbers will divide this 103. How are we going to go about it? This is where tests of divisibility that we may have learned in school will come of use. So what is the test of divisibility for 2? Whether it's an even number. 103 is certainly not divisible by 2. It's not even. Test of divisibility for 3. Sum of the digits should be divisible by 3. So this number is not divisible by 3. Test of divisibility by 5. It's evident the number should end with a 0 or with a 5. 105 is not divisible by 5. The only place where we need to spend some time is basically 7. There are methods for 7. Don't even worry. Just quickly look at the 7 table and finish it off. 14 sevens are 98. 15 sevens are 105. That is all that you need to know. Essentially, 103 is not divisible by 7 either. So 103 is not divisible by 2, not divisible by 3, not divisible by 5, not divisible by 7. So what do we infer from this? If this number 103, had it been divisible by one of these 4 numbers, it would not have been prime. Because it is not divisible by any of these numbers, because none of these numbers divides 103, 103 is prime. Quickly recap the 4 steps to determine whether a number is a prime number. The first step is compute its approximate square root. Integer level square root is good enough. Even if you go one aage piche, it's not going to make any difference to your computing. Second thing, are you going to check for all numbers? No. List down primes up to the square root. Third one, use test of divisibility of whatever you know to determine whether those numbers, those 2, 3, 5, divide this number. For numbers for which you do not know, do an approximate table and find out whether it divides or it does not. Lastly, if any one of these primes had divided 103, 103 would not have been prime. Because none of these numbers divided it, 103 is prime. So I would suggest, if you're shaky about this, just go to Google and check out list down prime numbers from 300 to 400. Just take those things, keep it aside. Ask your friend to give you a set of 3 or 4 of those numbers and then mix it up with 3 other 4 other numbers. Check out whether you're able to figure the answer right. Or if you're even lazy to ask a friend, just pick those 3, 4 prime numbers and check it. Go to the approximate square root. Let's say you have a number like, let's say 351. You need to check out whether it's prime or not. So till which point are you going to go? 19 square is a 361. So we're going to go up to 19. So we don't even need to check for 19. So list down primes up to 19 and check for this. That's all that you're going to do. Check for 3, 4 numbers. Check from 300 to 400 or 700 to 800. So you get practice with this. Shall we move on from here? Moving from prime numbers, moving on to odd and even numbers. Know the definition of it. Again, let's get clarity on it. Let's have a crystal clear definition. What is an even number? An integer that is divisible by 2 is an even number. -6 is even, -2 is even. There are negative even numbers. And positive numbers, obviously these are all even numbers. What are odd numbers? An odd number is 1, which when divided by 2 will leave a remainder of 1. Any of these numbers, when you divide it by 2, will get a remainder of 1. Odd numbers could be negative, odd numbers could be positive. Obviously, the question, if you have not figured out right now, talked about even numbers in the positive negative, talked about odd numbers in the positive negative, have safely ignored one thing, which is 0. Is 0 odd or is 0 even? What is the definition of an even number? Think about it, figure the answer. We'll just discuss it in a couple of seconds. Definition of an even number is it should be divisible by 2. Now comes the next important question. What do we mean by divisible? Let's say a number A, when it is divided by B, we'll say A is divisible by B if it basically satisfies 2 conditions. The first one, which all of us keep repeating, the remainder should be 0. Wonderful. Second important thing is that the quotient should be an integer. Only when these 2 conditions are satisfied will we say A is divisible by B. Let's apply this test on 0. 0 divided by 2. What is 0 divisible by 2? It is 2 by 0 is what is not defined. So if you're getting a little confused about it, 2 by 0 is not defined. 0 by 2, the quotient is 0. Is it an integer? Certainly yes. What is the remainder? The remainder is also 0. So does it satisfy this condition? It satisfies it. So 0 is even. If some of you thought it is neither, that is incorrect. 0 is certainly an even number. Right? So have this clarity. So in a data efficiency question again, if you think about even numbers, don't start by thinking at 2, 4, 6. There could be a -2, -4, and there could very well be a 0. 0 is an even number. Let's look at quickly operations on odd and even numbers. Sum of 2 odd numbers. Whenever in doubt, just don't even try to mug this up. I'm just going to quickly run through it. I'm going to use examples to help us proceed. Addition or subtraction essentially means one and the same. Let's pick 2 numbers. 5 is an odd number, 3 is an odd number, 5 plus 3 is equal to 8. So this is equal to even. So sum of 2 odd numbers or difference between 2 odd numbers will always be even. We'll quickly run through this exercise. I would suggest that you pause the video at this point before I start writing and run through this once in your mind so that you know how to arrive at it when in doubt. Right? Even plus even or even minus even. 4 minus 2 is going to be equal to a 2. 4 plus 2 is a 6. So even plus or minus even will be even. When you have a mix of odd and even, the result is going to be odd. Let's take a 5 plus 3. 5 plus 4. 4 is even, 5 is odd. This is going to be equal to 9. So this is odd. Whether it is odd plus even or even plus odd, it's essentially one and the same. Let's go with a 4 plus 3. This is going to be equal to 7. 4 minus 3, which is equal to 1. All of these will be odd. So both odd, both even, addition, subtraction will give you even. One odd, one even, addition, subtraction is going to leave you with an odd. Odd into odd is odd. 3 into 7 is equal to 21. It is not just 2 odds. You multiply any number of odds. All of them are odd. The final result is going to be equal to odd. Even into even will be even. 4 into 2 is equal to 8. So this is even. Any number of even numbers, it's not just 2. You multiply 20 even numbers, the product is going to be even. More importantly, even is like a drop of poison in a pot of milk, whatever you can call it, whatever the saying is. You have n number of odd numbers. You just add one even to it. The final result is going to be even. Because so many odds will give you one odd, multiplied with an even will give you an even. For example, a 2 into 5 is equal to 10. So if all numbers are odd, product is odd. All numbers are even, product is even. Any number of numbers, you just drop in one even into it, the product is going to be even, right? So keep this in mind. You don't have to remember it. You can just plug in some examples. Just be sure that you pick the right example. Don't do something like the way I did. 5 plus 3 will leave you with an incorrect answer because 3 was not even, right? Just watch out for those little things. Move on from here. Look at, again, definition of things that we know, but let's get clarity on this. Positive numbers and negative numbers. Positive numbers, any number that is greater than 0 is a positive number. When we think of numbers, more often than not, we always think about integers. There are infinite numbers between 2 integers. Between 1 and 2, there are infinite numbers. So don't be partial only to integers. in data sufficiency, the trap is usually laid when we think about only integers. So think of numbers like 0.01, 0.5, 8.5. All of these are positive numbers. What is the definition of a positive number? You add a positive number to another number, its value increases. I have a 10, I add a 0.01 to it, the value of 10 increases. Such a number is called a positive number. Negative numbers, any number that's lesser than 0 is a negative number. Again, these need not be integers. They are integers as -1, -2, you have -0.5, -0.01. All of these are negative numbers. You add a negative number to another number. Take a 10 and add a -8.5 to it. It will take away value from 10. It's going to result in a 1.5. The number reduces in value. That is what is known as a negative number. Obvious question, if you have not guessed it by now, what is 0? Is 0 positive or is 0 negative? Definition of a positive number is it should increase the value of the number. For example, if it's a positive number, 10 plus p will be greater than 10. If the number is a negative number, 10 plus that negative number will be less than 10. The value will go down. When I add a 0 to 10, what happens to it? Its value remains unchanged. It doesn't increase, it doesn't decrease. So is 0 positive or is 0 negative? 0 is neither positive nor negative. Quickly recapping the concept that we looked at earlier. Is 0 odd or even? 0 is certainly even. 0 is neither positive nor negative. Let's move on. We'll look at quick operations on positive and negative numbers. Addition of, we'll look at each of these sets. Just quickly, I'm going to read that, give a 10-second gap, and then answer it. So you have time to find out the answer in your mind before we proceed in the video. Addition of two or more positive numbers. Is it going to be positive or negative? That's what you need to figure out. Two or more positive numbers, the sum is going to be positive. Addition of two or more negative numbers. When in doubt, take an example. Take something like a -4 plus a -3. What happens to it? This becomes a -7. So addition of two or more negative numbers will be negative. Third one, addition of one positive and one negative number. The answer is cannot say. It's a function of the magnitude of which is greater. For example, a 5 plus a -3 will be equal to a 2. A positive number added to a negative number. Same thing, a -5 plus a 3 will be equal to -2. The magnitude of the positive number is larger, the result will be positive. The magnitude of the negative number is larger, the result will be negative. The magnitudes are equal. 5 plus -5 will be 0. So addition of a positive and a negative number, we cannot say. Addition of two positive, always positive. Two or more positive. Two or more negative, always negative. A mix of positive and negative, we cannot say. Let's look at subtraction. What happens in this case? Subtraction of one positive number from another. In always, this exercise we are doing to help you get a hang of looking for exceptions always. Data sufficiency accounts for 1/3 of the GMAT, and this 1/3 of the GMAT is all about exceptions. It's all about being meticulous. Right? 5 minus 2 is equal to 3. Looks like it's positive, but 2 minus 5 is equal to -3. I'm subtracting one positive number from another. 2 is a positive number from which I'm subtracting another positive number 5. The result is negative. So same 5 minus 5 will be equal to 0. So subtraction of one positive number from another, the answer is actually cannot say. Subtraction of one negative number from another. Now that you got a hang of it, quickly, what is going to be the answer? Again, the same cannot say is the answer to it. Right? If you have a -7 from which if I'm subtracting a -8, minus of -8 becomes +8. So the result is going to be positive. Similarly, -8 minus of -7 will be a -1. If it is -7 minus of -7, it would have been 0. So we cannot say subtraction of one negative number from another negative number without knowing their magnitudes. You cannot answer it. It's more interesting with the third one. Subtraction of one positive number from a negative number. You get the answer? You're going to subtract a positive number from a negative number. So my negative number, let's say, is a -5. Let's take a small enough positive number. Positive number is 2. I'm subtracting from it. What do we get? We get a -7. I get a 12 here. This is going to be a -17. So if you subtract a positive number from a negative number, the result is going to be negative. Right? It's already in the negative territory. We are taking some more from it. It's going to go deeper into negative. I had a 5 lakh loan. I'm borrowing 12 more lakhs. I'm down 17 lakhs. Right? So unless I'm like one of those few industrialists who can borrow a lot, this is not a good number to be in. Move on to the fourth one. Of one negative number from a positive number, we're going to subtract a negative number from a positive number. Quickly, we have a positive number 10, from which let's subtract a large negative number, say minus 15. 10 minus of minus 15 is equal to a 25. So if we subtract a negative number from a positive number, the result is going to be positive. We did addition, we did subtraction. More often than not, don't try to remember any of these things. This is just to get you to learn how to look at these things when you see it in an examination. Let's look at multiplication. It's interesting. 2 or more positive numbers multiplied obviously is going to be positive. Odd number of negative numbers, right? If I multiply minus 3 into minus 7 into minus 11, this result is going to be negative. Even number of negative numbers multiplied, the result is going to be positive. Negative into negative will be positive. Again, I have another negative into negative, will be positive. Positive into positive will result into positive. So even number of negative numbers will be positive. One positive and one negative will be negative. This is what you need to keep in mind, right? So again, all of these things, just take some examples, look for exceptions. Whenever this appears in a data sufficiency, always tell yourself there should be some trap, which is why they've asked it. So if you're doubting it, then there is a good chance you'll figure out those exceptions pretty well. Move on from this positive and negative numbers. Quickly recap the classifications of numbers that we did. This kind of a subset diagram will help us keep this in mind very well. First one, natural numbers. This is the most cohesive set of numbers to talk about. Within this, we can classify this as prime and composite. We can classify it as odd and even. All of these are subsets within this. Right? Now, the next one, if we add a 0 to the natural numbers, it becomes whole numbers. If we add, these are actually integers, positive integers. And then if we add negative integers also to it, that set is called integers. If we add fractions to it, that's called rational numbers. The set of rational numbers definition is they are fractions. Whatever is not a fraction is called an irrational number. Set of rational plus irrational numbers taken together will give us a set of real numbers. Right? So this is a classification that you need to keep in mind. More importantly, little things that 0 is an integer, it's even, neither positive nor negative. Rational numbers or fractions, integers are rational numbers. These little things, if you can keep in mind, it's a good chance at least 20-30% of the common mistakes that we do with data sufficiency questions can be happily avoided. Move on further. This is a term which we need to keep in mind. Certs, what are certs and their conjugates? Any number which is something like a square root of 5 is called a cert. Root 5 plus root 3 is called a binomial quadratic cert. Don't worry about those names. We'll get started. Root 2, root 5 are called certs. For every number of the form a plus root b, its conjugate is a minus root b. You multiply a cert, a binomial quadratic cert, with its conjugate. So a plus root b into a minus root b. This is how the form x plus y into x minus y. X plus y into x minus y is x square minus y square. So this will be an a square minus of root b square. The final answer is a square minus b. For every root a, for every a minus root b, a plus root b is its conjugate. Vice versa. A plus root b, a minus root b is a conjugate. For a minus root b, a plus root b is a conjugate. So product of a minus root b and its conjugate will also be a square minus b. This need not be a rational component. This could very well be an irrational component. This could also be a cert. So it could be a root a plus root b. Its conjugate is root a minus root b. So the result is going to be root a square minus root b square, which is a minus b. For every root a minus root b, its conjugate is root a plus root b. So the result is going to be the same, a minus b. Why is this of use? Again, there's never going to be a question in GMAT which is going to say multiply this number root 3 plus root 2 with its conjugate and give me an answer. What might happen is you might find the answer to something, and that answer that you would have got would resemble something like this. You would have solved an equation, would have got root 7 plus root 6 divided by root 7 minus root 6. Then you look at the answer choices. None of the 5 answer choices match what you've got. Does it mean that you got something wrong? No. Probably you're seeing the answer in a form which is different from this. Let's quickly look at how to make sense of it. For every root 7 plus root 6, we'll look at its alternative ways, which again has the same value. So how am I going to get that? I'm going to go about it in 2 variants of it. In the first one, I'm going to be multiplying with the conjugate of the denominator on the numerator and the denominator of this fraction. What is the conjugate of the denominator? For every root a minus root b, root a plus root b is its conjugate. So let's multiply and divide with the conjugate of the denominator. So this is what we're going to be left with. So the denominator is x minus y into x plus y, which is x square minus y square. So the denominator is very friendly right now. Root 7 square is a 7. Root 6 square is a 6. So 7 minus 6, the denominator becomes 1. What happens to the numerator? It's x plus y into x plus y, which is essentially x plus y the whole square, which is an x square, which is 7, plus y square, which is a 6, plus 2 into xy, which is 2 into root 7 into root 6. So answer is 13 plus 2 root 42 divided by 1. So you might see an answer choice, which will say 13 plus 2 root 42. This is the same as root 7 plus root 6 by root 7 minus root 6. There's no difference. You could find it in a slightly different form. We multiplied it and divided this fraction by the conjugate of the denominator. We can do it by the conjugate of the numerator as well. Right? Just try it at home. The answer that you'll get will be 1 by 13 minus 2 root 42. So root 7 plus root 6 by root 7 minus root 6 is the same as 1 by 13 minus 2 root 42 is the same as 13 plus 2 root 42. So all of these mean one and the same. So get conversant with the idea that your answer is not necessarily wrong. You're seeing it in a different form. That's the only thing. Again, some definitions to help us go. What is a factorial? For non-negative integer n, n factorial is a product of all numbers from n all the way down to 1. So 4 factorial will be equal to 4 into 3 into 2 into 1. Quick properties about factorial. The product of k consecutive positive integers is divisible by k factorial. And the value of 0 factorial is equal to 1. So basically looked at some definitions, things that we need to do, places where we need to have clarity on the definition. All of these are covered and done. Let's move on to part 2 of this. Just give me a minute when I change the slide back. We're going to be looking at reminders, divisors, division. Let's get clarity on it. Let's start with absolute basics. Let's look at a very typical simple division. We're going to divide a number 58 by 10. 58 divided by 10, it's a very simple division. Just how many times does it go? 5 times. 5 into 10 is 50. What are we left with? We are left with 8. So just name all of these different numbers that we see here. What is 5? 5 is the quotient. What is 10? 10 is the divisor. What is 8? 8 is the remainder. One thing is still left. What is this 58? This 58 is called the dividend. So these are the 4 components of your division. What do you mean by the quotient? The quotient tells you the maximum number of divisors that is contained in this number or in the dividend. So how many tens are contained in 58? 5 tens are contained in 58. That is what it is all about, right? Now let's move on to the second thing. After having counted all of the tens, did we go empty-handed? No, there is still something left. That is called the remainder. Whatever is left after counting all possible divisors, that's a most operative word, right? We are not going to say 58 by 10. You can say 4 tens I've got, and then I've got an 18. We won't say 18 is a remainder of this division because 4 is not the quotient. When we talk about quotient, we're talking about what is the maximum number of divisors that can be counted in this dividend. So the remainder in this case is equal to 8. Let's just put this entire thing in a practical example, right? John has $58 with him. He buys $10 chocolates. He goes to the shop with $58. How many $10 chocolates can he buy? If he wants to buy as many chocolates as he can, he'll be able to buy 5 chocolates. That 5 is our quotient. Now, after having bought 5 chocolates, is he going to come home empty-handed? He's still left with some money. And that is our remainder. So this is the basis of division, right? Have this clarity in mind. We're going to be looking at a few more ideas around this. And let's get complete clarity on that as we proceed. Right? Whenever you see a question on division, reminders and everything, try and write that question in a standard framework. That's a good starting point that helps you crack a lot of these questions effectively. What is that? We're essentially going to put this, instead of division, we're going to be writing this 58 in terms of the quotient, divisor, and the remainder. How do I write it? 58 is equal to 5 into 10 plus 8. Essentially, I'm saying if I go with $58, I'll be able to buy 5 $10 chocolates, and I'm going to come home with $8. So let's put all of these things. The number or the dividend is nothing but the quotient, which in our case is 5, into the divisor, which is 10, plus the remainder 8. This is what is known as the standard framework for any division. You see a question which says that a number x divided by 42 leaves a remainder of 17. Immediately write it in the standard framework. Let's look at a few more examples, and then let's proceed so we get conversant with this idea. N divided by 7 leaves a remainder of 5. Get started this way. It's a very nice way to start. N, you're dividing it by 7. You're getting a remainder which is equal to 5. Something is missing. That's a quotient. Let's say the quotient is equal to q. So what do we have here? The number n can be written as 7q plus 5. That is what is the standard framework of writing this number. Divisor into quotient plus the remainder. I'm going to leave you with 3 examples. Just take 10 seconds to quickly plug them in. I'll read them out for your benefit. A number p divided by 15 leaves a remainder of 12. A number q divided by 37 leaves a remainder of 21. A number x divided by 101 leaves a remainder of 70. Did you finish this? Here are the answers. The first one, if you want, we'll do it in this form. P divided by 15, 12 is the remainder. Let's say A is the quotient. So P is equal to 15A plus 12. The second one, Q divided by 37. Let's say B is the quotient and 21 is the remainder. So Q is equal to 37B plus 21. And lastly, X divided by 101. Let's say C is the remainder. C is the quotient. 70 is the remainder. So X is equal to 101C plus 70. So get conversant with this entire idea. You'll find that a lot of questions on divisors and reminders actually become very easy once you're able to write it in this form. Now that while we are at reminders, let's get some more clarity on the range that the reminder can take. What is the range of values for the reminder when a number is divided by a divisor d? Let's just go with the example that we had. Right? John went with $58 with him. He wanted to buy $10 chocolates. So he will buy as many chocolates as he can buy. So we realized he bought 5 chocolates. Number of chocolates bought were 5. The reminder you have is 8. What is this reminder telling you? The reminder is telling us that he has some more money left with him, but that money is not good enough for him to buy an additional chocolate. Only if he has another $10 will he be able to buy one more chocolate. If he had $50, he would have bought 5 chocolates, come home happily with no money and 5 chocolates. If he had $60 with him, he would have bought 6 chocolates, come home with nothing. If he had $62, he is not going to buy 5 chocolates and come home with $12. He will actually buy 6 chocolates and come home with $2. He is going to pack as many chocolates as he can with the money that he has got. So he'll exhaust as many chocolates as he can buy. And whatever is left is going to be a number that cannot account and buy him a chocolate. Which means these numbers that are reminders will not be something like 12. If it's a 12 when the divisor is at 10, you will obviously buy one more chocolate. So these values of reminders will always be less than the divisor. If he could have another $10, he will have another chocolate instead of $10. He is left with money that is less than what he can pay to buy a chocolate. So reminders always take values which are less than the divisor. So can it be a 0? Certainly yes. If he went with $50, he would have bought 5 chocolates and come home happily with 5 chocolates and 0 money. So the reminder could be a 0. And it can go anything up to d minus 1. You can't even have a remainder of 10, because if you had a remainder of 10 when the divisor is 10, when the value of a chocolate is $10, I'll buy a chocolate. John will buy a chocolate. He's not going to go home with 1 chocolate less and $10 in his pocket. So the remainder cannot even be the divisor. It will take values from 0 to d minus 1. So keep this perspective in mind. What values can it take? It can take values which range from 0 to d minus 1. It cannot be equal. It cannot be greater than the divisor. So for example, if you read something like, say, an x is equal to 15k, where 15 is the divisor, plus 23, then this 15 is, this k is not your quotient. It should have actually been a k plus 1. So you should probably write it as 15 into, let's say, an n plus an 8. This 15 should have, this 23 will buy one more 15 for us. And the actual remainder is going to be 8. So your remainder will never be greater than the divisor, will not also be equal to the divisor. Right? Have this perspective. Let's look at one other thing which usually comes to haunt some of us once in a while. What is the divisor in this case? What is the remainder in this case? I'm dividing a 3 by 8. I'm not dividing 8 by 3. 8 by 3, all of us know. The quotient is 2 and the remainder is also 2. This is not the question. What is the remainder? When 3 is divided by 8. This is what we have. Let's go with John's example. It's a beautiful example. John goes with $3 in his pocket. He goes to a shop and then he realizes that what he wants to buy costs $8. Let's say he wants to buy a bottle. Why I'm using this is I don't want to give you any opportunity to give a part of it. You can't break a bottle. You have to buy a full bottle. So with $3 in hand, will he be able to buy an $8 bottle? Obviously not. So he is not going to buy any bottle. So he is going to come home with 0 bottles. Will he lose the $3? John is smart. He's not going to lose the $3. So he's going to come home with $3. So the quotient in this case is 0. The remainder in this case is a 3. Just one more minute. It'll take one more iteration to help this understand better. Let's go with $11 with John. John goes with $11. How many $8 bottles will he be able to buy? He'll be able to buy one of those. He's left with $3 right now. So how many 8s are contained in 11? There is one 8 contained in 11. What is he going to come back with? He's going to come back with 3. He comes home and then his wife says, oh, this bottle is beautiful. Go and get one more. So this guy does not refill his wallet. He goes with $3 right now. Obviously, he's not going to be able to buy any more of these bottles. He'll walk home with 0 and he'll have $3 in his bucket. So the remainder, when 3 is divided by 8, is a 3. The quotient is equal to 0. So whenever, this is the key takeaway, when the divisor is more than the number that is being divided, the quotient is 0. You will not be able to buy any $8 bottles with just $3 with you. So what is going to be the remainder? You're not going to lose this $3. You're going to you'll come back with this $3. So the remainder is the dividend. So when I have a 7 divided by 17, what is the remainder? The remainder will be 7. If the dividend, if the numerator is less than the denominator, the remainder is going to be equal to the numerator. Little things keep in mind. A lot of us will think that if 1 by 2 is equal to a 0.5 and the remainder is 0. This is incorrect because if you remember a little while ago, we said the quotient has to be an integer. I go with $1 in my pocket. I'm trying to buy a $2 product. How many of those will I be able to buy? Nothing. What will I come back with? I'll come back with 1. So this is the idea behind reminders, divisors, and quotient. Right? Let's move on from here. Look at the third idea. Just give me a minute when I change the slide back. We'll start with what are factors, what are multiples. And again, today is all about definition and getting clarity on the definition. Many a times we are so fussy about the definition that you end up getting things wrong, or when you solve a question, you come out saying that could it be this way or could it be that way? So we're going to get clarity on these things. Start with factors of 30. What's a factor of 30? Any number that can divide. I'll write it here. 30 divided by its factors should give you an integer as a quotient and should have 0 as the remainder. That is what is known as a factor. Will 1 divide 30? It certainly will divide 30. Quickly write down these. 2, 3, 4 is not going to divide it. 5 will divide it. 6 will divide it. 7, 8, 9 will not divide it. 10 is going to divide it. And after this, the next number that will divide it is going to be a 15. And lastly, the number 30 is going to divide it. So these are all the factors of 30. So I'm going to put these definition, whatever we have written here, in words. Any number that divides 30 without leaving a remainder is a factor of 30. This is the definition that we all talk about. We miss one important point, and that point is about the quotient. An additional point to note is that the quotient of the division should be an integer, right? Otherwise, this number f is not going to be a factor of the number n. Now, whenever we are writing these factors, don't write the way I wrote it, right? So this would probably, you will miss some of these factors. A beautiful way to write factors is always to write them in sets of 2. Right? When you write a 1 as a factor, quickly write 30 as a factor, because 1 into 30 will give you a 30. If you spotted 2 as a factor, then the next one correspondingly will be 15. 2 into 15, 3 into 10, 5 into 6. The next number we're going to be talking about is 6, which is already written. So the moment you have crossed half the way, you have done the complete process. You don't need to wonder what is the factor once you've written half the number of factors. So anytime you have to list down factors, list them in sets of 2, list them in pairs. You're not going to list them like the way I listed the original time when I did it. Right? Let's move on. What are multiples? Multiples of pretty simple. We've done multiplication tables all our lives. Multiples of 6 are 6, 12, 18, 24, goes on up to infinity. The infinite multiples for a number. Some properties, some ideas about it. 6 is a factor of 30, then 30 will be a multiple of 6. If A is a factor of B, then B will be a multiple of A. 2 is a factor of 8. 2 is a factor of 8. 8 is a multiple of 2. So these factors and multiples are like parent-child kind of a relationship. 30 is the smallest multiple of 30. Look at the multiples of 6. What did we start with? We started with a 6. For 30, what is the smallest multiple? That is going to be 30. What is the largest factor of 30? It is 30. Any number is its smallest multiple and its largest factor. So have this perspective. So sometimes don't make a mistake. For example, if you're trying to find out something like the LCM of 30 and 18, you cannot say the LCM of these two numbers is 6. Multiples of 30 will start from 30. Multiples of 18 will start from 18. How can you have a multiple which is common to these two numbers which is lesser than that? So always keep these little perspectives in mind. So sometimes when you err, when the exam pressure, these pointers will help you correct course. A factor of a number is never larger than it, and its multiple is never lesser than it. It's a beautiful question that follows it. Is 1 a factor of all numbers? Looks like yes. We'll discuss it. We'll look at a few more examples, right? Some beautiful thoughts for us. This is a question that I'm keeping it at the end. We'll discuss it. But before we come to this question, I want to go through some more examples. Start with this example. Is 12 a factor of 48? 48 divided by 12. The quotient is 4. The remainder is 0. Is the quotient an integer? Yes. Is the remainder 0? Yes. So is 12 a factor of 48? Certainly yes. Right. Why did it take so long? Just going through it. Indulge me for a while. Let's look at the second one. Is 2 a factor of 4.4? Looks like it. 4.4 by 2. 4.4 by 2 is equal to 2.2. Looks like it's a factor. Hold on. Don't jump. Don't forget the definitions that we have. What did we say as a definition? A number f is a factor of a number n when two conditions are satisfied. The remainder should be 0. The quotient should be an integer. When 4.4 is divided by 2, the value is 2.2. Think about it this way. You're going with $4.40 with you. How many $2 bottles will you be able to buy? You'll be able to buy two $2 bottles. Will you have some money left with you? You'll have 40 cents or $0.4 left with you. So is the remainder in this case 0? Remainder is not 0. So is 2 a factor of 4.4? The answer is a no. Right? So keep this in mind because there are questions where you will think that 7.2 is divisible by 2. No, 7.2 is not divisible by 2. 7.2 when divided by 2 will leave you a quotient of 3 and a remainder of 1.2. There's absolutely no doubt on that fact. Right? Keep this in mind. What is the third one? What are the multiples of 0.5? Multiples of 2 you know, multiples of 5 I know, multiples of 0.5. What is a multiple of 2? 2, 2 into 2, 3 into 2, 4 into 2. That's how it's going to proceed. So what will be the multiples of 0.5? 0.5, 2 into 0.5, which is 1, 3 into 0.5, which is 1.5, 4 into 0.5, which is 2. So this is how multiples of 0.5 work. So multiples of a number n will be n, 2n, 3n, 4n, so on and so forth. It's as evident as simple as that. Here comes a more interesting question. This one. What are the factors of 0.5? This is a little tricky. Let's go back to our definition. 0.5. Let's say f is a factor of 0.5. What are the conditions it should satisfy? Remainder is 0. That's known to us. What is the other condition? The quotient should be an integer. Quotient is an integer. Write it once more. 0.5 by its factor will be an integer. Am I right in saying this? Yes. So 0.5 divided by an integer will all be its factors. So 0.5, what are the factors of 0.5? 0.5 by 1, 0.5 by 1 is 0.5. Is 0.5 a factor of 0.5? Certainly yes. 0.5 by 2, will it be a factor of 0.5? Yes, this is equal to 0.25. Think about it this way. 0.5 is 50 cents. Is 25 a factor of 50? Certainly yes. So 0.25 is. 0.5 by 3 will be a factor of it. 0.5 by 4 will be a factor of it. These are all the factors of 0.5. Now, How many 25-cent chocolates will I be able to buy with 50 cents with me? How many $0.25 chocolates will I be able to buy with $0.5 with me? I'll be able to buy two. So is 0.25 a factor of 0.5? Yes. Let's come to our interesting question. The question is this, I'm sorry. How many $1 chocolate will I be able to buy with $0.5 with me? I'll be able to buy none. And I'll come home with 0.5. Quotient is an integer, but the remainder is not 0. So is 1 a factor of numbers which are not integers? The answer is no. Is 1 a factor of all numbers? No. 1 is a factor of all integers. It's not just 0.5. Even if I went with $1.5 with me, how many $1 chocolates will I be able to buy? I'll be able to buy one. I'll come home with 50 cents. So 1 will not be a factor of 1.5, nor is it a factor of 0.5. 1 is a factor of 5, 1 is a factor of 7, 1 is a factor of 2, 1 is a factor of all integers, 1 is not a factor of numbers which carry a decimal. Right? Have this perspective again in mind. Quite important. I'm trying to clear out all common doubts that we have in this discussion of today. Move on further. Factorizing numbers. How do we factorize a number? Factorizing number is essentially writing a number as product of two or more smaller numbers, two or more of its factors. 30 can be written as 6 into 5, can be written as 15 into 2, can be written as 10 into 3. So this is what is known as factorizing a number. 6 can be written as a 2 into 3. Let's look at some larger number. Let's look at something like 72. Let's write 72 as a product of two numbers in few ways. Right? One very easy way to start is 1 into 72. Let's list down the factors in pairs. That itself is good enough. 2 into 36 is the second one. 3 into 24 is the third one. 4 into 18 is the fourth one. 6 into 12 is the next one. 8 into 9 is the last one. The next one is going to be 9. 9 into 8 has already been covered. So these are all the different ways in which I can express 72 as a product of two numbers. This is what is known as factorizing 72. Let's move on from here. This is where the most important concept comes. We'll try and write these, right? We wrote these 72 as a product of two of its factors. Just pick a couple of them. Let's go with something like 4 into 18. I'm going to take this. And I'm going to go with a 6 into 12. Both of these will give us a 72. Now, what we'll do is we'll try and write each of these 4 and 18 in terms of their prime parts. 4 is not prime, so it's going to be a 2 square. 18 is also not prime. 18 can be written as 2 into 9. 9 is not prime. We'll write it as 3 square. Let's club all like prime factors together. So it's going to be a 2 cube into a 3 square. So this is 72. When we wrote it as a 4 into 18, we can bring it down to 2 cube into 3 square. Let's check out what happens when we write the 6 and 12 in terms of their prime factors. 6 is a 2 into 3. 12 is a 4 into 3. 4 is not prime, so let's write it as 2 square into 3. Club the 2's, it's going to become a 2 cube. Club the 3's, it's going to become a 3 square. Just check both these things. 72 was a 4 into 18, was a 2 into 36, was a 6 into 12. But any one of these different ways that we wrote, if you prime factorized it, we wrote it as an 8 into 9. 8 into 9 is nothing but 2 cube into 3 square. It's the same thing. So you can express a number as a product of two factors in multiple ways. But when you finally break them down all to prime factorized, it can be expressed. The prime factorization of 72 is going to be the same single answer, irrespective of what was your intermediate step. It is going to be 2 cube into 3 square. A lot of questions in number properties. We will therefore prime factorize it. We'll express numbers in terms of prime factorization is going to be our starting point. Right? This is the fundamental theorem of arithmetic. Prime factorization of a number is unique. So if you bring it down to its prime factorized version, you will see it as one single way. 6 into 12 or 4 into 18 all mean the same, which is 2 cube into 3 square. So this is the starting point for a lot of questions. Take some more practice, right? Prime factorize the following numbers: 36, 48, 248, 108, 388. Try out these. I'll do a couple of them here. 36 is basically a 4 into 9. 4 is not prime. You can write it as 2 square into 3 square, right? This is one thing. 48 is a 16 into 3. This is going to be equal to 2 power 4 into 3, right? Try out the remaining ones. This is one way of doing it. I would suggest you go with this method. There is another method, which is a textbook school method. What we'll do is we'll start with the 36. We'll look at the smallest prime number that we know, which is 2. Will 2 divide 36? Yes. quotient is 18. Divided by 2 is going to be a 9. Will 2 divide it? No. Will 3 divide it? Yes. It's going to be 3. So basically 2 square into 3 square is your 36. This is time consuming. We don't have so much time. Steps carry 0 mark. So start somewhere. Yeah, 12 into 3 is good. 4 into 9 is good. 6 into 6 is good. Start anything that strikes you first and then prime factorize going forward. Right? Try out these 3 at your time. If you want, pause the video, note these things, and then move on. Quickly summarizing what we have discussed about factors, multiples, and prime factorization. Any number can be factorized in multiple ways, but prime factorization of the number is unique. If A is a multiple of B, B will be a factor of A. Prime factorization is usually the starting point for many questions in number theory. And before we wind up, for the nth time, I'm going to repeat this. A number A divided by B, unless the quotient is an integer and the remainder 0, B will not be a factor of A. A will not be a multiple of B. Right? So don't write something like a 2.2 here and then say that 4.4 is divisible by 2. That is not going to work. Right? Let's move on from here. Right. We're going to be looking at how to find out the HCF of two numbers. Right. It's a how class. We are not going to look at what it is. We are not going to look at when to find HCF. It is just a how. It's a basics. Let's get clarified. Let's clarity on that. It's a 3-step process. First step, prime factorize the numbers. What is the HCF of 36 and 48? We're going to prime factorize both 36 and 48. 36, we have done it earlier. 36 is equal to 2 square into 3 square. 48 is equal to 2 power 4 into 3. So prime factorized both these numbers. Right. Now, let's list down common prime factors from this to find out the HCF. 2 is a prime factor of both the numbers. 3 is also a prime factor of both these numbers. So we've listed down both these things. How do you find out the HCF? The third step gives us a HCF, which is pick these prime factors in their lowest power. The powers of 2 in both these numbers are 2 square and 2 power 4. 2 and 4 are the powers. The smaller of these two powers is 2. So I'm going to pick 2 square. For 3, in 36, it's a square. And for 48, it's a power of 1. I'm going to pick the lower power here. So 2 square into 3, 12 is the HCF. So quickly, for any set of numbers you're going to find out, it's exactly a 3-step process. Prime factorize all these numbers. List down only common prime. If I had something like, for example, if this number had been a 180, we would have had a 2 square into 3 square into 5. Right? In that case, I'll just pick only 2 and 3 because 5 is present in 180, but it is not present in 48. So we're going to pick only common primes. After having picked common primes, you're going to look at them in their lowest power. Lowest power of 2 between these two numbers is the square of 2. Lowest power of 3 between these two numbers is power 1. So 2 square into 3, 12 gives us the HCF. Quickly recap it in a printed form here. The prime factorize both these numbers, 2 square into 3 square. 48 is a 2 power 4 into 3. The next part, pick primes common to both, which is 2 and 3. Next step, pick the lowest power of 2, which is 2 square. Lowest power of 3, which is 3. HCF is nothing but the product of these two, which is equal to 12. So HCF, we covered how to. We'll look at quickly LCM and look at the how to of it too. Prime factorize, we're going to find out the LCM of 20 and 24. Prime factorize both 20 and 24. Starting point many a times is prime factorization. 20 is a 4 into 5. So that's going to be 2 square into 5. 24 is an 8 into 3, which is a 2 cube into 3. In the case of HCF, we picked common primes. In the case of LCM, we're going to list down all primes. The different primes that we are seeing are 2, 3, and 5. List down all of them. What is the LCM? LCM is a product of all primes in their highest power. All primes 2, 3, 5. What is the highest power of 2 that we see in these numbers? 2 cube. 3 and 5 have appeared only once. So we're just going to go with whatever is available. So 2 cube into 3, which is equal to 8 into 3, 24 into 5. 120 is the LCM of these two numbers, 20 and 24. Quickly sum it up in a printed form. How do you find out the LCM? 3-step process. First one, prime factorize it. 20 and 24, prime factorize as given above. The second step is basically we're going to list down all the primes. Third step gives us the LCM. How do we go about it? We're going to find out the product of the highest power of these primes. Highest power of 2 is 2 cube. Highest power of 3 is 3 power 1. Highest power of 5 is 5 power 1. Multiply all of these three, you'll get the LCM, which is equal to 120. One last recap about HCF and LCM. For both of them, the starting point is prime factorization. HCF, you go with common primes in their lowest power. For LCM, you're going to go with all primes in their respective highest power. The product of these will give you the HCF and the LCM. Right. Next month, when we are looking at the next session, I'll be focusing on linear equations, quadratic equations, things basics about algebra, what are absolute value, and we'll look at the likes of that. And if time permits, after all of that, we'll also step into elementary coordinate geometry and geometry. Right? If we manage to do it in next month itself, we'll have only 2 sessions for this basics. If it goes beyond that, then we'll essentially look at a third session. Right? So this completes basics part 1. Thank you guys. Wish you all a very happy new year again. Before I wind this session up, one last bit of advice, right? A good GMAT score goes a long way into converting your resume into a good admission. Don't compromise on the school that you do your MBA in. An MBA is done once in a lifetime, and you're doing an MBA to shore up your aspirations, right? If you're happy with what you are, if you're happy with your status quo, you would not be venturing into GMAT. You're venturing into GMAT because you want to go up in your career. And that is not going to happen with any MBA. An MBA from a good school is what will get you that. And how do you get into a good school? All things being equal, you can't go and change anything about your previous academics. You can't change the company you're working for. You can't change the number of years of experience you have. The only thing that you have in hand, or probably 2 things that you have in your hand, is 1, your GMAT score. Second is how you present your case in your application essays. Second comes later. The first bridge to cross is the GMAT. So do justice to your GMAT. GMAT is a very crackable examination, provided you put in the effort. Many of us have a lot of aspiration without having the willingness to work towards it. Right? So take a resolution this new year. 1, you'll set your goals high. Don't settle for anything that is mediocre. Second, commit yourself to achieving that. There is no point having an aspiration without working towards it. Aspiration without working towards it just leads to frustration. And don't let that happen. Right? With that note, I'll call it a day. Thanks for being a part of the session.